Welcome to today's paper reading. Today's paper is titled, Adaptive Correspondence Scoring for Unsupervised Medical Image Registration. This paper was published on AR14 by Xiaoran Zhang and colleagues from Yale University. The abstract introduces an adaptive training scheme for unsupervised medical image registration. Existing methods primarily use image reconstruction as the supervision signal. However, factors like noise, covisibility, and inconsistent image acquisition can lead to a loss of correspondence between images. To address this, the proposed framework reweights error residuals using a correspondence scoring map, preventing the parametric displacement estimator from drifting due to noisy gradients. This approach was tested on 3 registration architectures across 3 datasets, consistently outperforming other methods with statistically significant improvements. Deformable medical image registration aims to accurately determine non-rigid correspondences through dense displacement vectors between source and target images. This process is crucial for medical image analysis, such as tracking disease progression for diagnosis and treatment. However, the lack of ground truth displacement makes this a challenging problem. Classical methods are computationally expensive and time-consuming, limiting their practical utility. Recently, learning-based approaches have been widely adopted for their speed and state-of-the-art performance. These approaches often operate in unsupervised settings or use segmentation masks in a weakly supervised manner. Figure 1 illustrates the challenges faced by existing approaches in medical image registration, which assume uniform intensity constancy and covisibility across the entire image. This assumption leads to irreconcilable penalties during training, particularly in regions with large error residuals due to the absence of correspondence, as highlighted in the red box. Our proposed approach addresses this issue by reweighting error residuals with a predictive correspondence scoring map. This adaptive reweighting results in a smoother optimization process by reducing the influence of outlier regions, ultimately leading to improved registration performance. In the field of unsupervised medical image registration, several key approaches have been developed. Balakrishnan et al. Proposed an unsupervised learning framework using UNet as the displacement estimator. This framework ensures intensity constancy by minimizing the mean squared error between the warp source image and the target image, updating the parametric displacement estimator through gradient-based optimization. Various extensions to this architecture have been proposed, including adding diffeomorphic regularization, jointly learning amortized hyperparameters, and learning contrast invariant registration without acquired images. Additionally, recent advances in vision transformers and diffusion models have been integrated into these frameworks to enhance performance. In image registration, we have a source images and a target imageit. The goal is to estimate a displacement vector field U that maps pixels from the source to the target image. To achieve this, an objective function is minimized, which includes a data term data that measures the difference between the target and the transformed source image, and a smoothness term that penalizes large gradients in the displacement field, modulated by a hyperparameter lambda. The displacement field is estimated using various neural network architectures, including convolution-based, transformer-based, and diffusion-based models. The adaptive framework proposed by the authors incorporates a predictive correspondence scoring map to prevent displacement estimation from being dominated by error residuals due to nuisance variability. This is achieved by an adaptive weighting term that can be integrated into the conventional loss function for unsupervised training. The unsupervised correspondence scoring method predicts a soft map to show the degree of correspondence existence from the target image, which is optimized alternately with the displacement estimator to prevent a trivial solution where all scores are 0. Additionally, a momentum-guided adaptive smoothness regularization is introduced to adjust the degree of regularization based on the training dynamics, using an exponential moving average to compute the momentum of residuals, which guides the diffusion regularizer. Figure 2 illustrates the training pipeline of our proposed adaptive scoring framework for image registration. The process begins with estimating the displacement U from a pair of source and target images is/it. This displacement is then used to apply a spatial transform, resulting in the warp source images x plus U. Prior to calculating error residuals, the framework estimates a correspondence scoring map from the target image. This scoring map is utilized to adaptively weight the error residuals during gradient-based optimization. The detailed training strategy is outlined in Algorithm 1, ensuring the framework effectively integrates the scoring map to improve registration performance. In this section, we discuss the datasets used for testing our proposed framework. We utilize 3 different cardiac datasets, including 2 2D public datasets with MRI and ultrasound modalities, and 1 private 3D dataset. For evaluation, we use 3 key metrics: Dice coefficient score, DSC, Hausdorff distance, HD, and average surface distance, ASD. All experiments were implemented using PyTorch on NVIDIA V100/A5000 GPUs, with a UNet backbone for the scoring estimator. The code is provided to ensure reproducibility. In the quantitative evaluation, our proposed method consistently shows improvement over baseline methods. This improvement is not only observed in the DICE scores but is also statistically significant, as confirmed by the paired t-test results with p-values less than 0.05. On the qualitative side, the warp source images demonstrate a clear visual improvement, with our method accurately identifying regions of low correspondence and effectively preventing the displacement estimator from drifting. This dual approach of quantitative and qualitative evaluation validates the effectiveness of our proposed framework. Figure 3 presents a qualitative evaluation of our image registration method against the second-best approach in each dataset. The top 2 rows show results from the AC/DC dataset, while the bottom 2 rows display results from the CAMU dataset. Each block, delineated by black solid lines, contains source and target images with myocardium segmentation contours. The top row displays the original images, and the bottom row showcases a head-to-head comparison of the warp source images, is X plus U, between our method and the second-best method. The yellow highlights indicate the ground truth ES myocardium. DICE scores are reported in the subtitles, demonstrating the effectiveness of our proposed method in capturing more accurate correspondence across different modalities and frameworks. Figure 4 provides a qualitative visualization of our proposed framework within the voxelmorph architecture, applied to the AC/DC and CAMU validation sets. The third column showcases successful matching, supported by the estimated displacement shown in the fourth column. However, the error map in the fifth column highlights the presence of residuals. Our predicted scoring map, featured in the sixth column, effectively identifies regions with low correspondence and prevents the displacement estimator F theta from drifting away, as evidenced by the reweighted error in the last column. Figure 5 illustrates the training dynamics of the mean error residuals, denoted as T, and the adaptive momentum-guided weight, denoted as MT. On the left, the mean of error residuals T is shown, which is calculated according to equation 5. On the right, the adaptive momentum-guided weight MT is displayed, which is defined by equation 7. This figure demonstrates how these parameters evolve during training, reflecting the dynamic adaptation of the weight MT in response to the changing characteristics of the error residuals. This evolution aligns with the design objective of progressively enhancing smoothness penalization as training progresses towards convergence. Figure 6 illustrates the training dynamics of our proposed unsupervised scoring term LUX and regularization term Reg. On the left, the training loss curves of LUX in EQ3 and Reg in EQ4 are plotted, showing that both terms can be minimized jointly. On the right, the sensitivity of our voxelmorph-based approach to hyperparameters alpha and beta in EQ9 is examined. The study reveals that while the hyperparameters are not highly sensitive, fine-tuning them can yield better results, with changes within approximately 1% DICE for various alpha and beta values. This figure highlights the stability and robustness of our approach in handling different hyperparameter settings, contributing to its effectiveness in unsupervised image registration tasks. Table 1 presents a comparison of contour-based metrics, specifically DSC, %, HD, VX, and ASD, VX, to evaluate the registration accuracy of our method across various architectures and datasets. The data indicates that our method consistently enhances registration accuracy, outperforming other methods in terms of these metrics. This improvement underscores the effectiveness of our approach in capturing more precise correspondences, as validated by both quantitative and qualitative evaluations. Table 2 presents an ablation study on the impact of different loss terms on registration accuracy. The study reveals that removing the reg term results in a degenerate solution where the scoring estimator G outputs all zeros. The table compares the dice similarity coefficient, DSC, Hausdorff distance, HD, and average symmetric surface distance, ASD, across datasets ACDC and CAMU. It highlights the effect of the smooth term on improving registration accuracy. The results underscore the critical role of each loss term in achieving optimal registration performance. Table 3 presents the results of a paired t-test comparing our proposed method with the second-best method from Table 1 for each dataset in terms of DSC. The p-values indicate that our method's improvement is statistically significant. Specifically, for the ACDC dataset, the p-value is 5.85 times 10⁻16, and for the CAMU dataset, it is 0.01. This table highlights the effectiveness of our method in achieving statistically significant improvements over existing methods like voxelmorph, transmorph, and diffuse morph. The statistical significance underscores the robustness and reliability of our approach in handling medical image datasets. Table 4 evaluates the effectiveness of the momentum-based weighting MT as described in equation 8. The table presents metrics such as dice similarity coefficient, DSC, Hausdorff distance, HD, and average surface distance, ASD, for both the ACDC and CAMU datasets. These metrics are crucial for assessing the performance of the weighting mechanism and improving the accuracy and reliability of the model's predictions. The upward trend in DSC and downward trends in HD and ASD indicate the positive impact of the momentum-based weighting on the model's segmentation and registration tasks. Table 5 presents the evaluation metrics for displacement, smoothness, and training time across different methods. The metrics include the dice standard deviation, which measures the variability in segmentation accuracy, the percentage of estimated displacements with a negative Jacobian determinant, JU, less than or equal to 0, which indicates the smoothness of the deformation, and the training time required for 300 epochs. The table shows that all methods maintain a smoothness percentage below 1%, ensuring physical plausibility and smoothness in the deformations. Our method, ADCS, produces smoother deformations in voxelmorph and transmorph, and achieves similarly smooth deformations in diffuse morph, with percentages below 0.1%. The training times are also provided, showing the computational efficiency of each method. The adaptive correspondence scoring framework proposed in this paper is designed to prevent the displacement estimator from drifting due to noisy gradients caused by low correspondence, which can be influenced by nuisance variables like noise or covisibility during training. The unsupervised correspondence scoring estimation scheme introduced includes both scoring and momentum-guided adaptive regularizations to avoid degenerate solutions and ensure the smoothness of the scoring map. The effectiveness of this framework has been demonstrated across 3 representative registration architectures, showing consistent improvement over other baselines on 3 medical image datasets with diverse modalities. While the framework shows promise, it does require hyperparameter tuning for each architecture on each dataset, although performance is not overly sensitive to this tuning. Future work aims to explore an amortized hyperparameter optimization scheme during training to reduce computational demands and further validate the framework on clinical datasets. This research is supported by the National Institutes of Health, specifically the National Heart, Lung, and Blood Institute, under grant number R01HL121226. Acknowledgement of this funding is essential to give credit to the organizations that support scientific research. Additionally, references are crucial in academic work as they provide the basis for the research conducted, demonstrate the importance of the work, and ensure proper citation practices are followed to avoid plagiarism. Thank you for watching.